So my name's Joe Stringer.
And my name is Jarno Rajahalme.
And we'll be describing really the state of the connection tracking work, firewalling, NAT, and all this kind of great stuff in OVS today. So really what I'm going to do is sort of motivate connection tracking, give you an idea for the kinds of things that that enables and why that's a foundational part of implementing firewalls in OVS. I'll give you an example of a basic firewall that you can build based on this functionality. And then later on, I'm going to hand it over to Jarno for some discussion on NAT and perhaps a little bit of virtual server sort of load balancing functionality. And finally, we'll summarize the actual status of all the patch sets today. So if we look at the motivation for a lot of this connection tracking work, what we're seeing is that there's a lot of pressure from people in OpenStack world, Kubernetes, a lot of these cloud management systems that live above OVS for an expanded set of features. And this includes firewalling, NAT, load balancing, DPI, which Frank mentioned earlier. But question is, well, how does connection tracking work into all of this? So if you look at the types of matches and things that are available in OpenFlow today and what's matchable in OVS, you could create a basic firewall and match on IP addresses and port numbers. But really what this would implement is what I call a stateless firewall. So if you're trying to do anything more complex, then there are certain things that aren't available with that. So one example might be for TCP connections. There's no way to match on the window parameters. And so you can't track whether packets are within window or not with the current OVS. And there are some other cases like that in the firewall. And in terms of NAT, if you can statelessly translate from one IP address to another IP address by simply rewriting it and adjust the MAC addresses. But it won't handle some cases like if you have an FTP connection where the control connection negotiates the IP addresses that the data connection of that FTP session actually transact upon. And so what you need to be able to implement these in a more accurate manner that will work across all cases is really some sort of a stateful solution. I mentioned also load balancing there. I think it's, in a lot of ways, particularly with virtual server, it hits the same issues as NAT does. So if we look at connection tracking, really what it allows us to do is to track a particular, I guess, 5-tuple or maybe more complex than that, but track connections and store some level of information about them within the data path. And what we do is we expose more generic concepts about those connections, like whether it's a new connection, whether it's been seen before, so an established connection, or in the case of the FTP example, if it's related. And so what this allows us to do is to really steer the microflows, if you will, differently based on a policy like whether it's new or established, rather than actually explicitly matching on the IP addresses, the ports, or the TCP flags. And the core piece of this is that we've spent quite a while trying to optimize getting good megaflow wildcards in the kernel to ensure that we aren't sending new connections up to user space all the time. And we don't want to undo all of that when we start to support these stateful services. So another point to this is that we can leverage existing work in the kernel with the NetFilter connection tracker. And that really sort of allows us to accelerate this. So naturally, this concept is useful for building all the firewalling and NAT functionality, which I'll go into more detail. So with connection tracking, the way that this works with the code that's out today, a packet will come into the OVS flow table. You can create a flow which will execute this connection tracking action. And what that does is passes the packet through to the data path to this connection tracking element. which can look up within some sort of a database, like the contract table here, to find out what we know about that connection. And initially, that will be nothing if we haven't told it to track any connections. But later on, it will accumulate information. So secondly, you can recirculate a packet through to another table in the OVS pipeline. And this provides access to all of the CT state, all the connection tracking state values that are available in the contract table. And finally, we expose this commit flag, which allows the controller to decide which of the connections that it's actually going to store in that database. So if we look at a basic firewall where we want to allow all traffic that comes from one port and only allow established connections from a different port, if we model this by accepting all connections from the first port and committing those into the contract table, then anything that's within that contract table is essentially it's an allowed connection. And so that's what this first flow on the example here would do. Then when the traffic from the reply direction comes, the first thing what we'll do is we'll match on this CT state is not tracked. So it hasn't been through the connection tracker yet. And we'll pass that traffic to the connection tracker, recirculating to table 1. The second to bottom flow here in table 1 would then match on, again, the import, or it could be other fields, and the CT state to say this is an established flow. So we're allowing established traffic in this case. And you can see the drop, the third from the bottom and the bottom flows there will drop all other traffic. So now if there's a new connection that comes from port 2, it will be disallowed. So I sort of pointed out track and establish, but I didn't actually explain what packet or connection states are available. So initially when a packet comes into OVS, in most cases, it will be what we call untracked. This is minus TRK. And what this says is that it hasn't previously been through the connection tracker. So when you send it through the connection tracker, it comes back and will have the CT state as tracked. And tracked packets, we can tell if it's part of a new connection, that's to say that it hasn't previously been committed to the contract table, or if it's part of an established connection, which essentially says that it has been committed to that table and we've seen two-way traffic for that flow, for that connection. There are other aspects like reply, related for FTP connections, so you can tell that a data connection is related to the control connection for that FTP session. And finally, there's this invalid flag, which matches essentially most cases where there's some sort of malformed protocol, or say it's TCP out of window, a variety of other situations like that. And not only that, so given that the invalid flag is a matchable flag, that means that you don't have to just automatically drop that invalid traffic. You could choose to send it to a packet logger of some variety or some other tool to inspect that further. So I've talked quite a bit about the CT state and the different fields that are available, or flags that are available there. There's also this new field, which is a zone. Each connection tracking zone is a logically separate connection tracking table. So if you commit a connection to one zone, then it won't show up in another zone until you commit it into that zone as well. And each of these is independent. The CT mark and label are metadata fields which you can store arbitrary bits of information, 32-bit in the case of a mark, or 128 bits in the case of the label. And there are various use cases for this. Well, one of them was shown off in Frank's talk about DPI, where he would classify a particular traffic through the DPI engine and then modify that connection's mark to, say, have a SSH bit set. And then you could steer that traffic differently based on that particular mark. And the same can apply for a label. And finally, there's a new connection tracking action. And the main thing that, so a lot of this was presented last year by Justin and Thomas, but one of the new things is that we now transparently reassemble IP fragments. So if you send IP fragments to the connection tracker, they'll assemble for the remaining of the pipeline, and then on output, they'll be refragmented to the original geometry. So if you pass no arguments to the contract action, it will just sort of let the connection tracker know, but it won't necessarily commit the connection to the connection tracking table. If it's already there, then it may account stats or change the TCP state. But if it's not already in the connection tracking table, it'll probably be a no-op. You see the zone there, so you can specify inside the CT action which zone it's going to apply to. There's support for ALGs. At this moment, there's only FTP, but that can be quite easily extended to other ALGs that are available, certainly in the Linux kernel. We have this exec action, which takes other sub-actions. So, for instance, set field or reg load or some restricted set of actions which allow us to apply the mark or the label. There's also this the table. So the table is the mechanism by which we actually expose the connection tracking state from the connection tracker. So if you don't specify the table, the packet processing pipeline in OVS will just continue, and for the remainder of the pipeline, you won't have access to the connection tracking state. But if you specify a table, it will make a clone of the packet and recirculate that into a later OpenFlow table. And then you can then match on that CT state, or you can manipulate it, or match on it and change the behavior of the packet based on that. And finally, there's this commit. So with that, I'm going to pass it over to Jarno.
Okay, so for last couple of weeks and now months, I've been working with the NAT feature, which is another part of the Linux kernel contract, which we haven't before integrated with. So let's motivate this from some of the use cases we've been hearing about, using OpenStack and working with containers. So OpenStack allows a persistent floating IP to be assigned for a VM in addition to a dynamically allocated fixed IP. And the VM itself never sees this floating IP. I believe it's currently being managed by the L3 agent transparently. Integrating NAT to OVS allows us to do the mapping between these two addresses. Similarly, maybe even in a agent node, or more interestingly, maybe distributed to the hypervisors themselves. So source NAT transforms the source address, and the destination NAT address transforms the destination address. So that's where the names come from. All NATed connections actually need both transformations. So in the original direction, for example, if the source address is NATed, then in the return direction, the corresponding destination address will need to be transformed back to the original address. Then another use case or example here is the Kubernetes services, which hide a pool of servers or pods behind a virtual IP address. And then there's a load balancer that chooses the server for each new connection. And this would be a DNAT use case. Port numbers can also be mapped, but if we don't specify a port range explicitly, this mapping will only happen in case of a port collision. So, so the NAT action here, it's an extension of our contract action. So it's an embedded attribute within the contract action itself. And for new connections, we need to supply the type of NAT we want to do. Is it source transformation or destination transformation? And then optionally, a port range as well. And all these new connections need to have the commit attribute in the contract action for this NAT state to be persisted. the NAT attribute can also be applied without any attributes, but then that only applies to existing connections. So here's the example for the OpenStack floating IPs. So here the VM has fixed IP and floating IP assigned, and the new packets on the top part for outgoing connections, we first go through the contract, and then after that we match on the CT state fields, and for the new packets the NAT action on the top right is applied where the source address is mapped to this floating IP. Can I have water? Yeah, thanks. Okay, so that's what happens on the green box on the top. The return traffic will be coming back from the right. First go through the contract action for connection tracking, which makes these connection tracking state fields available. And for established traffic, we go through the bottom yellow box and back to the VM on the left. So in that case, the reverse NATing of the floating IP happened in the first contract action on the bottom right. And the same happens similarly to the incoming connections from the public internet side on the red case where the destination address is NATed. For load balancing, in Kubernetes services, for example, and many other use cases, we have a virtual IP address, which is used by all the clients to use the service being provided by this group of servers, web service, for example. And then when we match on that destination IP address here, 10.1.164, we steer the traffic to a OpenFlow group table entry, which implements a select group, which makes a selection among the available servers. And in this case, the client 1 gets the server 1 marked in green, and this selection is persisted as part of the contract state and the NAT state within the contract NAT extension, so that the return traffic can be then reverse mapped properly. And here we see that another client would go through the same mechanism and get another server assigned. So a very basic use case for load balancing using NAT to store the connection state or the selected server, so that when the controller would then use OpenFlow to rebalance the traffic by resetting the weights of each bucket in this select group. And this could be based on an explicit feedback from the servers, the load feedback, or maybe based on the group stats themselves. And then when this kind of rebalancing happens, if you use some stateless form of load balancing, that would steer existing connections to possibly a different server. But by using the contract and NAT, we can keep the connections assigned to the selected server regardless of any load rebalancing events afterwards. So this is kind of a strawman proposal, how to do load balancing with the current facilities that we have. And testing with this, I noticed that we currently use a mechanism, hash-based mechanism for selecting the bucket, which hashes on both Ethernet addresses and the full 5-tuple, which means that we basically every connection goes to user space as a miss-up call. And we don't want to undo, as Joe said earlier, we don't want to undo all the good work we've done with megaflows. So basically, a solution like this is not production ready, but for performance reasons. And we need to investigate other means for selecting the buckets than hashing. So it could be round robin, weighted round robin, and all kind of stateful mechanisms like that become possible with the state that we store with contract. We can also use DP hash that we already use for bonds that has similar performance benefits than avoiding the full 5-tuple match. And that's it. Back to Joe.
All right, so I promised a summary of what the actual status of the patches was. And so in Linux 4.3, released a couple of weeks ago, the OVS contract support was merged in there. In terms of the OVS user space patches, the support in the OV Proto is all upstream in OVS master today, along with a bunch of system traffic tests, which tests different aspects of that interface. In terms of the kernel data path backport, which we supply for the OVS module in the tree, in our tree, that is under review at the moment, but we expect to merge it soon. Just this weekend, the DPDK user space data path series was posted, and so that will go through a review as well, and I think there's some plan to use that for the Windows data path as well. In terms of NAT, there's been RFC patch series posted, and we intend to continue to pursue that, merging that upstream. In terms of the DPDK and user space data path for NAT, support for NAT is that's as yet not explored, but it seems to be a natural progression. For the load balancing, as Jarno mentioned, that we have an idea, it may be possible today, but in terms of the performance implications, more investigation will be necessary to figure out a good way to actually implement this for instance, for the Kubernetes use case. So that's all I've got today. Any questions or comments?
All right, everybody, let's thank our speakers. And we do have time for questions. So if you have a question, please come to one of the microphones in the aisles here. I think maybe people are a little fatigued at the end of the day. So, yeah, please come.
Hi. Okay. So what about, so it seems to work pretty well. So what about the integration with OpenStack and Oven? Because what we want at the end is a stateful security group and get rid of the Linux bridge, right?
Yeah, I think probably Russell will be the good person to.
Sorry to jump up, but yeah, let me try to help answer that. There's I guess a couple of different places that can be integrated. One is that is the way that we implement security groups for OVN. So OpenStack using OVN as the network provider for Neutron. That's the way we implement security groups. That code's already merged. I mean, you have to, pending the state of the actual support, make sure you have the right kernel support available and everything. So that's that. The other thing is the existing OVS support, the original OVS support in OpenStack that could also be updated to use this for security groups. That's not done. There are people looking at that. I think that's been prototyped in the past, and I would expect that to be done there as well at some point in the next 6 months. But it's not there yet.
Okay, thank you.
Just a couple of questions. So the connection track, the tables used in the contract, is it separate from what OVS uses, or is it the same set of tables?
So if you're using the kernel data path, then it shares the same connection tracking tables as what the kernel does, the Linux kernel does, and so all the same tools, the contract, all that kind of stuff.
So is there any separation, like certain set of tables are used for contract and some for other OpenFlow, like table 0 and table, a bunch of tables are already reserved, right? Is it?
Yeah. So maybe I answer that question. So basically, the contract tables are totally separate from any other flow tables.
Okay.
They are not part of OpenFlow kernel module or OpenFlow user space. And what might be confusing, we have these zones going from 0, 1, 2, 3, and then we have talked about OpenFlow tables.
Correct.
0, 1, 2, 3.
Yeah.
They're different tables. OpenFlow tables exist in OVS user space only. In kernel, we only have one table of flows. And then in the contract, there is basically one huge table of contract entries, which then specify a zone per each entry. So logically, there are multiple tables one for each zone, but that hasn't been implemented that way. But the answer is that they're separate tables, and that's it.
Yeah, the second part is because there is persistence, do we have any limits on how many connections we can track?
Yeah, so it's limited by the same sorts of limits that Linux would be. So there are ways to configure that through sysctl, the standard tools that you'll see in Linux.
You talked about TCP window and how so my understanding of this particular talk is weak, but I have a concept level question. The impact of a TCP window when TCP flow has sort of gotten out of whack. There have been talks and papers written that particular flow doesn't just impact its own flow, but it impacts a bunch of other connections. And it slows down a whole load of connections that are coming into a particular server, let us just say that, to a NIC through virtual interfaces. My question is, and I don't know if it's a valid question, does contract and other stateful entities that you are discussing today able to track those anomalies?
So the way that it works today is that kind of traffic would be matched to this invalid bit. And so it's really pulled with any other sort of traffic that's marked as unexpected or outside of the expected range of connection tracking for particular protocols.
I would maybe add up to that it's up to the flow table, basically controller designer to decide what to do with this invalid packets. So they could be passed on as any other packets. And there, if you have any performance degradation in the server due to those invalid packets or out of window packets, you would still have that problem. If you decide that you'd rather drop those packets instead, then as far as the classification done by contract is correct, the TCP connection itself would not suffer from that because they were out of window anyway, and you maybe get some performance back on the servers if there was a degradation in the first place. So it's up to what you want to do with that classification that the contract provides for that protocol state.
One quick question I had is when using some of this functionality, and I noticed you had a note up there that said that sometimes you can actually get some influence from either the local networking stack or you can actually have state tracked from different zones potentially. Sometimes in some segmentation, we may want to actually track a packet twice. Is there an action at any point where you can actually have it forget that something was tracked at any point? So kind of like flush the CT state, like maybe, if you come in a specific port or you come in a specific bridge, the action to just forget any connection tracking state so you could reinitiate it and use a similar rule?
Yeah, at this stage, no. We've thought about it.
Okay, one more vote.
It's been requested, but And there are ways to get around that limitation, typically. For example, if you have like ingress and egress going to different zones, like to different VMs, maybe different tenants, you don't have to match on the track bit. If you already know that it's potentially gone through a different zone, you come to a specific table in your pipeline, which starts egress processing, for example. You could just commit it to put it through a contract action in another zone. And with some updates that are part of the NAT series, even if you happen to put it back to the same zone that you did earlier, nothing bad would happen. So you may not need that feature of clearing the state after all. So.
Regarding upstreaming the code to the kernel, where was the main roadblock for you? Just to make it quick, because I know that's a long story,
I'd say
but from your perspective.
IP fragmentation, how that was handled.
IP fragmentation.
Yeah.
We can do it. If you're interested, we can talk.
Yeah, feel free to come see it in those later. But, yeah.
So that being done, I'm pretty hopeful that the NAT piece, being just an incremental piece on top of what we already have, should be much, much faster to get through, hopefully.
Hopefully.
Okay, let's thank our speakers one more time.